everybody, and welcome to All Your Macs Are Belong to Us, the story of CVE-2021-30657. My name is Jaron Bradley, and I'm joined here today with a good friend of mine, Patrick Wardle from Objective-C. If you're into Mac security at all, then you very likely know his name, as he's the owner of a very large blog in the security community for macOS. So to get started, I'm going to pass it off to him, and he's going to give us a bit of research and discovery behind the bug.
Thanks, Jaron. So today's talk is about an intriguing vulnerability that impacted all recent versions of macOS. Before we dive into kind of the root cause analysis of the vulnerability, I first wanted to show you the bug in action. Now, before we do that, though, I do want to give credit to the original researcher, an individual named Cedric Owen, who actually discovered this vulnerability and passed it over to me for verifications and root cause analysis. So, as we can see on the slide, imagine a user has downloaded something from the internet. Perhaps they believe this is a resume, a required security update, and unfortunately, they click on it. Now, normally you would expect macOS to block malicious content, especially if it's unsigned or unnotarized. But as we can see here, there are no prompts, and as soon as the user clicks on what they believe, in this case, is a harmless resume, their system is inadvertently infected. So before we dive into the details of the bug, the flaw, the vulnerability, let's briefly talk about Apple protections that are built into macOS, because these are relevant because the bug was able to neatly sidestep, well, all of them. So it's important to understand how Mac users get infected with malware. And the reality is the vast majority require user assistance. So I like to kind of term these, user-assisted infection. And the idea is that the user is essentially coerced or tricked into running something they should not. And as Mac admins, I'm sure you are well aware of all these infection vectors. But there are things like, fake flash updaters, poisoned search results, users downloading pirated or Trojanized cracked applications. And, in the cases, we're essentially left with the user infecting themselves, right? They're tricked into what they believe is a required flash update, but as we all know, it's going to be malware or adware. Now, Apple really had to do something because Macs were becoming ever more prevalent, ever more common, especially in the enterprise. And arguably in lockstep, so were these attacks, these fake Flash player updates, poisoned search results, etc., etc. So there was a decent increase in the number of infections impacting macOS. And this is problematic to Apple for two reasons. First, sure, they don't like it when their users are getting infected. And also, it doesn't make them look good if, there's news articles or conference talks about Macs becoming infected. So Apple made the observation that, as we mentioned, the majority of these infection vectors require user interaction. So they said, what can we do to essentially protect the user from themselves? And they have introduced three main technologies: file quarantine, Gatekeeper, and Notarization, that we're going to talk about briefly. Now, it's important to understand that all these security mechanisms are rooted around the quarantine attribute. The quarantine attribute is something that is added to any file that's downloaded from the internet. And in short, when the user then goes to launch that item, if it has the quarantine attribute set, it will kick off these subsequent checks: the Gatekeeper checks, the Notarization checks, and the file quarantine checks. So first up is file quarantine. This was added all the way back in 2007. So almost 20 years ago-ish. And the idea is that it provides a simple confirmation to the user that what they are about to run is actually an application. And this is important because a lot of malware authors will try to hide their malicious creations as something benign. So for example, on the slide, we have what appears to be a PowerPoint presentation that the user might click on. In the proof of concept attack at the beginning of this slide, we showed what appeared to be a resume. In theory, file quarantine will pop up and say, hey, wait a minute, just to let you know, you're not opening a resume, you're not opening a PowerPoint presentation. This is in fact an application from the internet. Are you sure you want to run it? This was a good start, but unfortunately users would just click allow or open in the majority of cases, and thus still inadvertently infecting themselves. Apple then moved to something called Gatekeeper in 2012, and the idea was to simply block unsigned applications. So even if the user would download something malicious, when they went to run it, there would be a pop-up saying, hey, this is not signed. And if you look at the alert prompt, there's actually no option to allow it. So the user can't click OK. Again, though, a shortcoming is it required the code to be signed, so malware authors simply started signing their malware. Most recently, Apple has introduced notarization. Notarization is actually a really good step and provides a decent amount of security. The idea is that Apple will individually scan and approve binaries and applications before they are allowed to run on recent versions of macOS. So again, even if the user is tricked or coerced into running something malicious, if it has not been explicitly approved or notarized by Apple, the operating system will block it. And as you can see, I have hackers sliding into my DMs. This is the exciting life I lead, complaining about notarizations and saying, hey, look, this actually impacted our operation because, our binaries weren't notarized or Apple caught onto the fact that they were malicious and blocked them. So notarization, again, the most recent of these advancements in protecting users from infecting themselves, and arguably the strongest and most effective. Now, we wanted to talk about all those security mechanisms because the average Mac user, and perhaps even us as Mac admins, might lean upon those security mechanisms and believe that macOS is secure because Apple has introduced these security mechanisms and tell us they do a great job. But as we saw at the beginning of the presentation, this vulnerability was able to sidestep all of them. So now let's look into why this is the case. First off, the proof of concept exploit that we illustrated at the beginning of the talk is correctly quarantined. So this should mean that the file quarantine checks, the gatekeeper checks, and the notarization checks should be performed. Because again, the quarantine flag means the system has correctly identified that this item, our exploit, is from the internet and thus should be constrained by these security checks. We can check the code signing information of this and we can see that it's not signed. And also that means it's not notarized. So what does this mean? Well, this means we have an unsigned application that's not notarized, that is correctly identified from the internet, but is somehow able to bypass file quarantine, gatekeeper, and all the notarization checks, and is allowed to run with no pop-ups, no alerts, and is not blocked by the operating system. Again, this is really less than ideal. So now let's dive into this proof of concept to figure out exactly what it is and the root cause of the vulnerability. Because at the time it was unknown. Why is macOS allowing this unsigned, non-notarized application to be run? Should be blocked. So the first thing we notice is if we look at the proof of concept, it turns out it's an application. And if we look at some of the contents, we can see really two interesting things. First and foremost, it's missing the info.plist file. Now, if you're familiar with applications, the majority, if not all applications, have this info.plist file, which contains metadata about the application. But this one is missing. That's interesting. Also, if we look at the executable within the application, this is what gets run when the user double clicks on the item, we can see that it's not a standard binary, a mock-O binary, but instead it's actually a script. Very interesting. And it turns out this proof of concept or other similar applications could be created with the popular Appify developer script, which had no intention of actually creating a vulnerability or triggering a flaw, just a way to package up scripts to deploy them as applications. But kind of ironically or sadly, it would actually trigger this vulnerability as well. So I said, okay, cool, I have this proof of concept application. It's missing an info.plist file, and its main executable component is a script. I want to figure out ultimately why macOS is allowing this to run with no alerts. How is it able to bypass all these security mechanisms? Unfortunately, when you double-click an application, there is a ton that goes on behind the scenes. There are user mode daemons, there's daemons running as root, there are kernel components that all get involved that somewhere had a flaw. So instead of reverse engineering all of these, I said, all right, let me run applications that I know are blocked and the proof of concept, which is not blocked, and look at the output of the logging subsystem to hopefully pinpoint the daemon or the chunk of code that is problematic. So first I took a standard application that had a Mako binary and an info.plist file, ran it, it was blocked as expected. I then ran a script-based application that still had this info.plist file, and it was also blocked. Then I ran the proof of concept, which is this bare-boned application missing the info.plist file, and it has a script, and that one was run. So again, the idea is let's run all three of these and look at where the log messages diverge. First, though, we need to talk about enabling private logging. If you look at the logging subsystem on macOS, a lot of data is not printed to the logging subsystem. And since we want to see all the data, what we have to do is install a profile that basically tells macOS, hey, please log everything, because we're doing some analytics and we want all the information. Okay, so first up, I ran the standard application that had an info.plist file, and main executable is a Mako binary. These are standard applications. Again, recall this was blocked because it was unsigned as expected. And if we look at the logging output, we can see two important things. First, we see a daemon, syspolicyd, displaying a logging message that it is doing the evaluation. This is great. This means this is likely where the vulnerability lies. We then see that after a variety of checks, it's come to the conclusion and saying, hey, here is the evaluation results. I'm going to show a prompt, because this is an unsigned, trusted application. And this aligns with exactly what we saw. I then ran the second application. Again, this is still the unsigned one with the info.plist file, but has a script-based component. And the output is very similar to the previous application. Again, we can see scan results being shown, but there is an additional logging message saying script evaluation, which indicates there's a different code path if an application contains a script. And then finally, our proof of concept, the bare-boned application that has no info.plist file and has a script, we can see it goes down the same code path, but the scan results are different and no prompt is shown. So if we kind of summarize the result of these three different applications, we can see that when we run our bare-boned application, the proof of concept that is somehow able to bypass all these security checks, there's a logging message that says Gatekeeper evaluation result equals 2, where the other ones that are blocked have a Gatekeeper scan evaluation result of 0. So what is 2 and 0 and why does it matter? Well, first and foremost, if we look at the reverse engineer this daemon and look at its disassembly, we can see there's a method called evaluate scan results. And we can see it is explicitly checking the Gatekeeper scan results, and if it is set to 2, it's going to allow that, and we can confirm that in a debugger. So it just validates and confirms that yes, if the system decides that an application is of type 2, and we don't know what that is yet, it will allow it to run with no prompts, no alerts. So now we need to figure out where this type 2 comes from, because this is the problematic misclassification of our proof of concept application. So again, we continue the reverse engineering of the syspolicyd daemon, and we can see that there's various checks. Ultimately, there's a call into the isBundled subroutine. If we look at what this subroutine does, it just returns a flag of a previous check. So we go and check that code, and we see there's an unnamed subroutine who evaluates the application, and that is then passed into the isBundled method. So we want to look at that unnamed subroutine. And if we reverse engineer it, we can see what they're trying to do is make a determination if the item we're about to execute, the application, is a bundle or not. And how do they do it? Well, if we look at the code, again, extracted, reverse engineered from syspolicyd, we can see they're looking for an info.plist file. Again, if an item has an info.plist file, it will be classified as an application and be constrained by the checks, blocked if it's unsigned. But if the item does not have an info.plist file, like our application, our proof of concept, it will be misclassified and allowed. So again, just to wrap up the core flaw, the bug, if an application did not have an info.plist file, which is not required, and its executable is a script, you are able to, on a fully patched macOS system, bypass Gatekeeper, file quarantine, and notarization. This is obviously very problematic because it allows attackers to go back to their tried and true techniques of infecting users. So we were kind of worried about this, but as it turns out, it was even worse. And so now I'm going to hand it off to Jaren, who's going to talk about how we were able to discover this being exploited as a zero-day in the wild. Over to you, Jaren.
Great, thanks, Patrick. So let's get started with how we went about discovering this being actually used in the wild. So Patrick had initially reached out to me. I didn't have all the details of what was going on just yet, but he provided me with the information that, hey, it seems like if you execute a script as the main executable inside of an application, it seems as though you might be able to bypass quite a few protections. So he asked if we're able to kind of put a detection together to look for this type of thing, and we were able to do that pretty quickly. Before I get into exactly how we did that, it's important to understand how the Jamf Protect detections engine works. So for those who aren't familiar, Jamf Protect is able to take different behaviors that are occurring on the system, and it's able to turn those behaviors into standardized events that we can base logic on. So, for example, if a process is created on the system, we can look at the path of that process along with maybe the command line arguments that were contained inside of it. We can say if one of the command line arguments is this letter or that letter. We can say, if the signing info of this process is signed by so-and-so, we can perform all types of checks. And the same goes with files being modified, created, deleted, downloaded, anytime certain behaviors happen that are hooking the keyboard, all types of different events. We can perform logic on. So that's just a bit of an introduction to how Jamf Protect works, which you need to understand for how we actually put this detection into play. So naturally, we want to take a lot of the issues that Patrick just described, and we want to turn those into a number of checks. So you can read the pseudocode kind of at the top of this page, or I will walk you through it kind of step by step here. So we took the proof of concept app that Patrick had put together, and we could easily base a detection on this. The first thing we wanted to know is if a process was created. So this entire detect relies on a process being created because when you open an application, that's what happens. The second check that we're going to perform, we want to know if the current application that's executing is a script. We can easily check this by looking for an interpreter running. We can say if it was Ruby running, if it was Python running, if it was Bash, so on and so forth. We've confirmed that a script is indeed running. So continuing to use this proof of concepts, we can also, our next check is going to be that this script that was executed is also located within an app bundle. As that's another check that this vulnerability requires if it's going to be taken advantage of. So sure enough, we check that, and we can confirm this in a number of different ways. An easy way is to look at the path in which the executable was run from. If it's run from, if its path contains, contents macOS, and the parent folder of that is some type of .app, we've pretty much confirmed that. Finally, well, not finally yet, but the next check is going to be that the parent of this executed script is launchd. When you double click a program, an XPC message is passed off in the background, and launchd takes that application you've double clicked and it opens it. So our next check, more for false positive reduction, is just going to be that this app was double clicked and not so much executed from a terminal or something like that. Next check, we want to know if this process was opened for the first time and or is being analyzed by Gatekeeper. Because remember, the app does indeed get checked by Gatekeeper, it just happens to also pass all of the checks. So we can do this a number of different ways. There's some private APIs you can use to do this, or if you're doing it on your own. An easy way to perform this check is by checking to see if app translocation is in the file path of the executed script. This is just a temporary file path that gets created anytime you double-click a program for the first time after downloading it. So this is our next check. And then finally, and again, more for false positive reduction, we want to check if the name of the script that was executed exactly matches the name of the application. Again, this is primarily for reducing false positives. Remember, as Patrick kind of stated, legitimate applications can use scripts as their executables. That's perfectly fine and accepted by Apple. Naturally, like, we're going to be fighting off some false positives. And when it comes to detections, the more false positives you can reduce, the less time you spend wasting on pointless detections. So we try to be as tight on the detections as we can. So after taking this detect and releasing it and watching what was going on in the wild, I think it was about 2 days later, if that, it might have been 1 day, we received a detection that this detection had triggered. And this is kind of a look at the initial detection. You see that it was an M1 MacBook Pro. Bin bash is the path of the process, which is exactly what we wanted. The parent process ID is that of 1, which means launch D. And the process arguments, if we take a look at that, we can indeed see that the app translocation string is in there, and it's the application that was executed is called 1302.app. I don't know how many of you are developers that are watching this, but I'm guessing the odds are pretty good that you don't have an application that only consists of numbers in its name. That's pretty weird, just kind of sticks out like a sore thumb. Maybe it's not malicious, but of course this met all of our criteria for the 0 day. So we went and took a look at where this was downloaded from, and we grabbed a sample of our own. So what was kind of funny is that at this point I reached out to Patrick and I said, "Hey, I assume you kind of came across this 0 day because you found it in malware, right?" Not really thinking that we'd found something kind of groundbreaking. And Patrick said, "No, I found this because a friend reported it to me." And I said, "Oh, well, that changes things." So this was pretty exciting, and Patrick naturally asked for a sample, and I said sure, but you can't blog about it. Which, again, if you know Patrick, this is about the worst thing you can tell him. He loves to blog about all things Mac security, so got some concerns coming back in the text, but it was a complete joke, as you know if you've read the blog. There was a massive blog post on this very topic, so. So now we're going to take a look at the two different variants. So first off, after performing some analysis on this, we came to the conclusion that this is the Schlayer adware dropper that was using this. Yes, a 0 day being used inside of adware. Very curious and very interesting. But Schlayer is known to be one of the more aggressive pieces of adware when it comes to evading different security measures that Apple puts in place. So what you're looking at here on the left, you're looking at kind of an original variant of Schlayer. And on the right, you're looking at a modified version of Schlayer that's been modified to abuse this 0 day. And keep in mind, nobody knew this 0 day existed yet. Like this wasn't public news yet. So on the left, one way you can bypass Gatekeeper is by right-clicking the application you want to open and selecting Open from that prompt. And Schlayer actually walks you through this process in its old variant. That's how it's getting users to install it and not signing it. It's literally just walking users through the instructions of how to bypass Gatekeeper. This is by design. Apple wants to allow you to install software even if they don't think it should be run. And Schlayer kind of just took advantage of this process and is directing users through it. On the right side, if you look at the 0 day variant of a very similar Schlayer payload, you'll see that all it says is double click to install. And that's because it's using the 0 day that no longer requires the steps to bypass Gatekeeper. So let's take a look inside that. Here we're looking at the directory layout of this malware. On the left side, we have something called installer that is basically a soft link to something else called install.command. .command will be a bash script of some type or something that should run in a terminal. And then on the right side, we see a very similar directory structure that uses a soft link, but instead the install is a soft link to the 1302.app. That 1302.app then has contents, macOS, and then 1302, which is a script. You'll notice inside this app, there is no info.plist. So everything is matching the criteria here. And we can basically tell by looking at this slide and the previous slide that the creators of Schlayer have specifically modified this malware to abuse this 0 day. They didn't happen to stumble upon it. They weren't abusing it without knowing, like we saw some applications doing. They had specifically taken their malware and modified it so that it would successfully abuse this 0 day. So here we're looking at the payloads and the differences between what would actually execute on the system. On the left side, you see the original variant where the Schlayer sample would include a resource fork. For those who aren't familiar, a resource fork is metadata that you can attach to a file. It was kind of initially created as a way to maybe include an icon in the metadata of your file. For those that are more familiar with Windows, it's very, very similar to the alternate data stream. But what Schlayer would do is they would include an entire encrypted zip inside of that resource fork. So when this script would run, it would access its resource fork, it would grab the zip file and decrypt it. After unzipping that decrypted zip file, we'd have a new executable that was dropped on the system, and that executable would then be kicked off by the malware. Now with the 0 day variant, very, very similar, but slightly different. Instead, what we see is the zip file being placed directly at the bottom of this bash script, kind of in its raw zip form. You can see the PK as the header there towards the bottom. But basically, the malware in this case will go to the offset of where that zip file starts, and it will grab the bytes and then unzip those bytes to a new executable and go ahead and execute it before killing the terminal so that it didn't display anything to the user. This would all happen in microseconds. It goes very, very quickly before the user even knows they're compromised. They've been compromised. So I think we also did see where this 0 day variant payload with using this zip file placed directly into the payload. We did also see that prior to this 0 day being used. I don't have these specific examples of those or samples, but I do believe we saw that, and I feel fairly confident about that. So I'll say Schlayer was also fairly lazy with this. A 0 day is a big, big deal, especially a 0 day that performs a bypass of 3 different technologies. So what I find very interesting is that the authors of Schlayer were just willing to burn this 0 day on this adware. If you take a look back, this is what virus total looked like back in April at the time of discovery. So even malware was already discovering Schlayer, and Schlayer just threw their 0 day in there like it was no big deal. So vendors continued to detect on this 0 day without realizing they were actually picking up a 0 day. A very interesting circumstance. I'd call that getting a little bit lazy. Usually when you find a 0 day, you might modify your malware very strongly so that your 0 day doesn't get caught. But the authors of Schlayer chose not to do that, and this is kind of the summary of the story of finding this malware in the wild. That wraps up my section on finding this in the wild. I'll now pass it back to Patrick, who will bring it all together.
Thanks, Jaron. Amazing stuff. So let's wrap up this talk with a few conclusions. So today we talked about an intriguing vulnerability, a logic flaw that impacted all recent versions of macOS, that would allow an attacker to neatly sidestep a myriad of foundational security mechanisms built into macOS. We talked about the underlying flaw, the cause of the bug, essentially If an application was not having an info.plist file, it would be misclassified and allowed to run. Jaren then talked about the fact how Jamf Protect was able to detect this vulnerability independently being abused by adversaries, malware authors, in the wild as a zero-day. Kind of scary stuff, but at the same time, pretty cool. I want to thank you for virtually attending our talk. Also, make sure you're always running the latest version of macOS. I should point out Apple did patch this vulnerability fairly quickly in more recent versions of macOS 11. But in the meantime, it's still probably a good idea to run a security tool like Jamf Protect, because without being able to go into too many details, there will be another talk in the future about a similar bug. So stay tuned and stay safe.